Well, thank you everyone so much for joining us for North Point Geographic Solution Geospatial Lunch and Learn. Today, Cray Freestone, one of our developers, is going to be doing a presentation, a deep learning on ArcGIS, Python API, and Atlas Living. So with that, I will turn it over to you, Cray.
Yeah, hi everyone. So, like Heidi said, GIS developer at North Point Geographic Solutions, like you can see right above me, but my head is blocking. And so we're just going to get started. We're going to start with going through workflow in ArcGIS Pro and doing a workflow in the Jupyter Notebooks that Esri has in ArcGIS Online. So the first thing you'll want to do before you start utilizing any deep learning is using the libraries that Esri has made really easy to install. Basically, all of the deep learning tools that are in ArcGIS Pro, you can't use unless your Python environment is ready to use them. And since it is a lot of separate libraries that need to be installed, you can do it manually in a Conda environment, or you can simply download one of these, a .msi file, some installer file, and it will get your environment all prepared for you. So what that looks like is if you go here and download it, and this is for ArcGIS Pro 2.6 and 2.7, and I imagine soon to be 2.8. If you have a version before then, they have instructions for manual installation in case you do run into that. So once you download that, you can extract the zip file. You'll find a MSI file. You will just double click that and you'll be good to go. It's really as easy as that. And it prepares your default Python environment to be able to use all of these tools. So it won't create any new Conda environments. It'll just put it in your normal ArcGIS Pro-Py3, which I believe is the default Python environment. And so from there, we can actually start using the deep learning tools. So in ArcGIS Pro, we have the detect objects using deep learning. So in this case, we're going to try to detect some building footprints. And before, you would usually have to try and train your own model. You'd have to prepare some my sound is cutting in and out just a little bit.
Yeah, we can still hear you. It just like gets quieter. So I just don't know if it's your mic or anything.
I'll try not to move my head around, but
you sound great right now.
Okay. So what you'd have to do before is you'd have to train some samples for your model. You'd have to draw a bunch of boxes around houses. You'd have to load that in to a model. You'd have to train it, and then you could use that model to then detect building footprints feasibly anywhere that matches, that looks similar to the area that you're training on. But Esri has trained a model for us, so we don't have to go through that. So what I did was, if you go into the Living Atlas, ArcGIS Living Atlas, you can just Google this, and you just search for DLPK files, which stands for Deep Learning Package. Esri has all of these pre-built ones. So today we're going to be looking at building footprint extraction, but they have a lot of other really cool ones that could come in handy, say for tree point classification, if you're doing a tree inventory in your town, road extraction. So there's a lot of cool stuff to check out here, but for right now, we're checking out building footprint extraction. And so it does give some information for how to go about it, any other relevant information. You can download it here from the Living Atlas page, which is what I did. You can also, in your model definition here in this tool, you can go into the Living Atlas and search for DLPK and find any of those right here. And the third way you can find it, if you want to, is go into your portal under your catalog pane, go to Portal, Living Atlas, search for DLPK, and you can then, there's usually a download option, and this worked for me before, so I'm not sure why that option isn't there, but those two other options are just as good. So what we'll do is, it's simple enough. Have an input raster. This is somewhere in Kentucky. Got this aerial imagery from kentuckyfromabove.com, which provides a lot of high quality satellite imagery and point clouds. It's a pretty cool website. And then you'll want to use your model definition, which in this case is going to be the building footprints. And it's going to fill out some arguments right here. So once that's loading, we'll go over it, but I'm going to try to load the environments. So there's going to be a few things that you have to adjust before you can actually use this, depending on your computer. If your computer is powerful enough, you might not have to adjust any of this, but for the sake of this computer that I'm on, it can't quite handle the defaults that are on there. So let me go to, also I should mention, if anybody wants to follow along with this presentation, you can go to this bit.ly URL and you should be able to see the same presentation. So that's 3BWZ2XC. And I'm just going to go back here. These are the arguments that it's going to put in there as the defaults. The batch size defaults to 4. And you can think of that as how big of a bite is your computer going to try and take at a time. You know, if you're thinking of how do you eat an elephant 1 bite at a time, you can think of this as your sort of bite size. Some computers might be able to handle a really big bite size of 4. Other computers, like the one that I'm on, can only handle 1 of 2. So it's basically how many CPUs or GPU processing power it's going to be using, which brings us to, in the environment pane, you should switch your processor type to GPU so it goes faster. I have tried to do this on a CPU and it goes very, very slowly. So if you do it on CPU, you don't have to mess with the batch size, but if you do specify GPU, it might crash if you try to do it at 4. But also, if your computer can do 4 or 8 or something like that, that's great. It'll probably go by a lot quicker. So here we got it loaded. I'm going to switch this to 2. In environments, I'm going to switch my processor type to GPU because it defaults to CPU. And cell size, you'll want to make sure it's the same cell size as the layer that you're doing the detection on. So I'm just going to switch it to that. I think in this case, it's 0.5. You can find the cell size under the properties of your raster. And you'll also want to set your extent to, I set it to the current display extent because I only wanted to do this area. If you want to do the entire raster, you totally can, just might take a while. And the rest of these, you only really need to mess with batch size and threshold. The rest of these aren't super important for this webinar, but threshold is on a scale of 0 to 1, how confident does this deep learning model need to be before it returns results? So the threshold is 0.9. It is 90% sure that it is going, what it is returning is a building. So you're going to get less results with a higher threshold, but you'll probably have more accuracy. But if you lower it, you can get more results, but they might be less accurate. So I ran it a few times just to see what that would look like. So in this instance, this is the default, what it would return. We can see that it definitely detected buildings, but it also definitely missed a lot of buildings that we wanted. Similarly, 0.5, or yeah, threshold of 0.5 does gets a lot of information, but also makes some pretty funky shapes. It might have some false positives. I ended up settling on 0.7, which still had some funky shapes, but sort of got me where I wanted to be. And right now, this is pretty good, but it doesn't really look what we think what building footprints would look like. We kind of want them to be a bit more regularized, which that is good because there is a regularized building footprint tool, which you can just put in your footprints that you want in here. It'll spit out a feature class wherever you want it to go. Keep the method at right angles, and you can mess around with the tolerance. I believe I did a tolerance of 1.5 in order to get this, which looks pretty good, but it might depend on your area, what the output of your previous tool looked like. So it's going to take some playing around, but Esri really has made this sort of deep learning very accessible inside of ArcGIS Pro, and there's plenty of other models that are out there too that you can use in here from the Living Atlas. Now to go to part 2, which is slightly less accessible, but is still, I would say, overall more easy than trying to go your own route with some other deep learning libraries that are in Python, is using the arcgis.learn library to do some time series forecasting. So let's see if it will load here. Esri put out a sample notebook for time series forecasting, univariate, meaning they're only looking at one variable when they're trying to forecast, and it's going over detecting rain. So in this instance, I'm going to be going over detecting code compliance cases in a local municipality. So every summer in this municipality, they get a lot of complaints for tall grass and trash. And every summer they have to hire on additional staff to address the increased workload, sometimes double or triple of what they're used to over the winter. So it might be good to have a model that you could predict in the upcoming summer, how many people will I need? So let's try restarting this. Okay. So first step is importing all the necessary libraries. Also, this is going to be at the end of the presentation. So if you want to follow along, you want to delve deeper into this, you totally can, and I can come back to this link later if you aren't getting it right now. But so right now I have my feature layer of code compliance cases. I'm just putting into what Esri calls a spatially enabled data frame. It's like a pandas data frame, except that it has location, although in this instance, I'm not really using location. I am filtering it, so I'm filtering it. Does it still sound all right, or am I cutting out again?
Oh, you just came back.
Just came back, all right. Sorry about that. I'm filtering it, so I only am getting the tall grass or trash yard, inoperable vehicles, dead trees on private property. These are all the nuisance cases in this community. Specifying for a certain date, 2006 and 2020, so we got 14 years of data. And I am just grouping them by week. Just want to know what the weekly count is for each week. And this is the end result of that. Gives me a good idea of what the weekly counts are. You can definitely see there's a seasonality to this. This is all summer. A low point of about maybe 25 cases in a week to a high point of about 600 cases in a week. And here I'm just sort of cleaning it up a little bit. So for training the model, Esri has a, let's see here, actually, scikit sklearn has a train test split function, which takes your data, splits it one into training. So that's what we're going to use to train our model. And then the test data set is what we're going to use to later check how well did we train our model. I'm setting the test size to 52. Since all this week is summed up, or since all the data is summed up into weeks, and there are 52 weeks in a year, and this is seasonal data, I am changing it to 52. Specifying shuffle equals false because I still want the data to all be in the same order because time does matter in this, and time is linear. So in this instance, prepare tabular data is a function from Esri, which takes your training data set, wants to know what the predictor variable is and what your index field is. So I got the count of cases, I got the date, that's the time aspect to it. And also with this prepare tabular data, while I'm not strictly using spatial data to this, you can put in spatial data if you want to. You can also put in rasters too if you're doing a sort of time series analysis on rasters. This is just on tabular, like non-spatial data, which I feel a lot of people have on their hand. Sequence length, again, is 52. And this is just showing all the batches that we're going to be feeding into our model. So we are building the model with our prepared data. We're specifying the sequence length as 52 because there are 52 weeks in a year. And the model architecture, there's 2 or 3 options on that. Inception time is the default, so you don't really even need to specify that here. There's a few other options. I hadn't tested out with other options. It seems like this one worked pretty well. Learning rate is the rate at which our model will learn, and you don't really need to know what that means. All that you need to know is that Esri has a function that will find the optimal learning rate for your data for you. So that is what I did. I found the learning rate, and I can plug that into our .fit method, which this is the actual training of the model. So I am running it through 100 times. You can just think of that as, it's called epochs, but you can think of that as the model going through your data 100 times and trying to learn from it. In this case, it worked out well, which we'll see in the results of the trained model. In other instances, 100 could be too many for your data because it could overlearn for your specific model. And if it overlearns for your data, it might not work on other data sets. It might be too specific to your data, and it might not be general enough to be applicable in other areas. So if it was overtrained, we would see this validation line be a bit higher than this training line. So in this case, it's looking good. Our model score is, the best score you can get is 1.0, so I will take 80.82. And then you can show the results of the model to see what the ground truth was versus what the prediction was. So we're seeing, some differences in 40 cases here, but the shape is overall pretty similar. The guesses are, they're pretty on par. And we can actually forecast based on the training data set near the end. So we've withheld all of the testing data, and we can then check out what would it look like compared to the ground truth versus the prediction, essentially. So the orange is that test data set that we withheld near the beginning. And then this is, the blue line is what our model predicted what that would be. So we can see that it's guessing a little low near its peak, but overall it's following a pretty sane pattern. Predicting the future sounds a bit dramatic, but it's pretty easy. you just call the dot predict, and the number of predictions will append a certain amount of rows on the end of your data frame. So in this case, I'm appending an extra 2 years onto the end of my data frame, 52 times 2, 52 weeks in a year. And since after this, I had prepared all this data, I could download some more to see how did these new predictions fare against real world data again, which is kind of the point of this, but I wanted to just test it out, see how it was. These are the next 2 years. This is what it guessed for April 26th of 2021. And we can see that it got, pretty close. So I would say the most important part of all of this is knowing how to then save and load the model, because it would be a bummer to have to train your model every time you want to get any predictions. Once you have a model and you are feeling good about it and you just want to predict based off of it, you probably just want to save it and load it for later. So Esri makes it pretty easy. You can just hit .save. And optionally, you can do publish equals true, which creates a DLPK file. And the DLPK file is essentially just a zip file. And inside of that zip file, time series, is a Esri model definition file, an EMD file. And from there, you can load the model into the .from model method or function. If you're doing this locally, or if you're loading it straight from ArcGIS Online, so this is if you want to load it locally, but if you want to load it from ArcGIS Online, you'd want to get the item ID. You would want to download that item. This function here, which I took from Esri's, somewhere in here. So this function extracts a zip file, and it just looks for an EMD file, and it returns that model path to that, loads it in, and then you can use your model to predict based off of whatever data you want. And this model was trained relatively fast with just one of Esri's standard notebooks. So they have a few notebooks here. Standard is, they say for light analytics, but it worked for time series forecasting just fine. And it's free. Advanced is more computing power, 3 credits per hour. And advanced with GPU support is 30 credits per hour, and could be good if you were actually using a lot of heavy deep learning stuff. I think for tabular data, you can get away with standard stuff. So I did a version with the GPU as well, and it was quicker, but in this instance, I don't think it made that much of a difference. But maybe if you're doing some stuff with point clouds, that would be good. So I'm going to go back here to the top, just in case anybody didn't get this URL, but that is all I have. I don't know if we wanted to, I know we have like 4 minutes, but if anyone had any questions, we can maybe do some questions or.
Yeah, I dropped the presentation and the notebook preview in the chat, so everyone should be able to grab those from the chat too. There aren't any questions in the chat, but if you want to either drop a question in the chat or unmute yourself in the and say it out loud, we definitely have time for a couple questions.
If there's no questions, that's all right. I know I went through it quickly, and I think it would be good to, spend some time, go through that notebook. Yeah.
Yep, and we'll make sure that the recording is sent out as well. Just give us a couple days to get it up on YouTube. And then if you do have any questions that come up afterwards, feel free to give Cray an email. So